Okay, today I want to get through resistors and capacitors in a circuit, RC circuits. Okay, now before we get going, let's just think back to what a capacitor does. It stores charge. Okay, as it stores charge, a voltage is built up on the, as charge builds up on the capacitor, a potential difference between each side of the capacitor forms. Okay, so now, two key things. Okay, we have our capacitor here, where that has a charge and a potential difference across it, and we say that that's equal to Q is equal to CV. Okay, now as that charge, the way that we've been doing it to this point, when we connect it to an ideal battery with ideal wires, okay, what happens is, we say we've got this battery, it's got this capacitance. If we did a loop of this, if we do a Kirchhoff loop of this, the voltage I gain across here has to be, and there's no current flowing because there's no resistance anywhere, this has to charge instantly. Because when I go around, I would say that my voltage gain there has to be matched by the voltage loss here, which is going to be minus Q over C. Okay? Q equals CV, so I solve for V, it's Q over C. So this is plus, this is minus, this is the positively charged to the capacitor, this is the negatively charged to the negatively charged end of the capacitor. Okay? And this would equal 0. And that's all fine and dandy. Okay? But we know that charges have to flow. In order for charge to build up on this capacitor, charge has to flow, there has to be a current. Now, for the above circuit, for this circuit that we just did, let's say that E is equal to 9 volts and C is equal to 10 microfarads. Okay, so we could connect this to a 9 volt battery. I'm going to say E is equal to 9 volts. I'm going to say the capacitance is 10 microfarads. That's actually a very decent sized capacitor. A lot of capacitors are in the picofarad range. 10 microfarads is not trivial. Okay, so let's just see how much charge builds up on here. So I have Q is equal to, looking at it from here, CV. V is equal to, well, we're calling it E here. So we could say 10 microfarads times 9 volts, because I'm going to keep, this is microcoulombs, I can keep the microfarads, so this will be 90 microcoulombs. It's actually a pretty large charge. But now, that 90 microcoulombs, let's think about this. I also need to give an internal resistance to the battery. I'm going to say that the internal resistance here, R for the battery, or BAT, I'm going to say is 2 ohms. Because I want to see how fast this capacitor will charge up. So now if I connect this, so if I say, all right, let's just figure out the current in here that exists, at least for the time being. So initially, before this has any charge on it, before it has any potential difference, in order for there to be a potential difference, there has to be a charge on it. If I do current will equal the voltage, which we're calling E, over that resistance. This is going to be 9 volts over 2 ohms, and that current's going to be 4.5 amps. This means every second this current is delivering 4.5 coulombs of charge. I only need 90 microcoulombs. If you want to figure out the time, remember the I is going to equal delta Q over delta T. So my delta T will equal delta Q over I. So now this is 9 times 10 to the minus 5 coulombs I is 4.5 amps, which is a coulomb per second. So 9 divided by 4.5 is 2. So my delta T here is equal to the time that it would take to charge if it stayed at this current, which it doesn't. This is just rough back of the envelope calculation here. 2 times 10 to the minus 5 seconds. Okay. It doesn't actually charge that fast, but it gives you the order of magnitude, and yeah, that's not going to take very long. Okay. So if we want a capacitor to charge up a little bit more slowly, a little bit more carefully, okay, we put a resistor in there. And we have to take a look at what happens to the capacitor and the loop itself as this charges up. Okay, let's take a look. Okay, we're going to be more specific about it. This is like they call it back of the envelope calculation, where you're just trying to get an idea for how long it takes to charge. Let's instead actually solve for a specific situation where I have with a bigger battery, with the same battery really, and with a much bigger resistor. Okay? So I'm going to make this circuit with that E, R, and a capacitor. Okay? Let's make E equal to 9 volts. I'll keep the capacitor at maybe I'll kick it up to 50 microfarads. And I'm going to make that resistor equal to, I don't know, we'll say 20,000 ohms. That is a pretty big resistor, but it's not unreasonable. Resistors we'll be using in class, we go up to 100 kilo ohms, and they're still little small things. Okay, it doesn't take much to make a resistor be that big. Okay, so now what's going to happen here? Current's going to come out of here. If I did a loop, remember, potential around any loop has to equal 0. So now initially, okay, I'm going to go say, so I'll say initially. This will develop, if I go across here, this will have the battery, E, the current minus IR, and then I have the voltage across the capacitor. But if that capacitor is initially uncharged, okay, remember that voltage across the capacitor is equal to Q over C. I'll rewrite it over here. And this has to all equal 0. E minus IR minus Q over C equals 0. Now, if the capacitor is initially uncharged, there is no voltage across this. So that goes away. And you simply have that the current is equal to E over R. Notice, with the really big resistance, the current is very small. I'll call this I0. If I have a very small current, it's going to take a while to build up charge on that capacitor. Now, at the end, okay, we'll say long, long time. So after a long, long time, this will charge up. We'll have E minus IR, okay, minus Q over C. But now, this will equal whatever the charge is here. Because as this charges up more and more, okay, it's going to charge up till it's the same voltage as the battery. So what happens is Q over C will equal the EMF of the battery. So if that's the case, IR has to go away. that IR right here has to go away to 0. So the current disappears. Now, one thing that I like to say when we're doing analysis of these circuits. Initially, a capacitor just acts as a wire. It acts like there's nothing there. Because the current just flows through like there's nothing going on. After a long, long time, and it develops that voltage on there, this acts as a brake. So when we get a break in the circuit, so no current can flow through here. So when we get into more complex circuits in class, if there's, we can just treat this as a hole in the circuit and we can't do anything more with it. That's after a long, long time. Initially, we treat it as a wire. Okay. Now, in between, okay, we can set up a differential equation. Now, everyone needs to be able to set up the differential equation. And in order to solve it, well, you're going to talk to Dr. G. I'll show you how to conceptually solve it. But in order to, but everybody needs to be able to set this up. Okay. So now, at any time, at any time t. Okay. So if I set that back up, E minus IR minus Q over C is equal to 0. That's my loop equation. Still valid. Let's rearrange a little bit. Okay. I'm going to push this over to the other side. So I'm going to say IR plus Q over C is equal to E. Rearrange a little bit more. I'm going to divide everything by R. I've got I plus 1 over RC times Q is equal to E over R. And notice I use lowercase I when it's going to be time sensitive. I is dq dt plus 1 over RC times Q is equal to E over R. Everyone needs to be able to get to that point. Okay? That is a, everyone should be able to set up the differential equation. You might not be able to solve it, okay? But everyone can set this up. Now, let's think back to over here. Initially, okay, so we need an equation that fits this. We need an equation for Q. Q is a function of time that will match this. Okay? Well, let's think about what happens. Q, initially, Q of 0 is equal to 0. Q after a long period of time, so I'll just say, we'll call it infinity, is equal to CE. So after a long period of time, if you solve for Q here, you get CE. Let's think of let's just use some thought as to what this would probably look like. Okay? Now, I could graph this. Let's just have some thought graphs here. Q of t, I know it has to get up to CE. It could go like this, where it's a straight line, and goes off like that. It could look like this. CE, this is Q, it's a function of time, curves upward, gets up to CE, comes across. I don't think those look very valid. Nature has them, but doesn't, where it can avoid, nature doesn't really like those kind of kinks in graphs. I think if you guys thought for a moment, you might be able to figure out what this is. This approach is asymptotical. It's going to look something like that. Okay. Early on, by the way, that slope of that line should be about, and that slope should be about the E over R. Okay. Then you can figure out for yourselves why that come to me with the answer request. But anyway, and that's only for initially here. That doesn't count for up here because the slope definitely changes. But early on, that slope should look like E over R. Now, let's take a look. We've talked about graphs that look like this before when we were talking about terminal velocity. The general form of this is going to be 1 minus e to the negative t. It has some kind of form like that. Okay? Because initially we want it to be 0. So if you take 1 minus e to the negative t and you plug in 0, you get 1 minus e to the 0. E to the 0 is 1. That equals 0. Good. Check. We're good there. So now, this is, let's say t equals 0. And now, we'll have t doesn't equal, it approaches infinity. Make math teachers happy. Have approach infinity. Okay? 1 minus e to the negative infinity. Okay? 1 minus e to the negative infinity would be 1 minus 0, which gives you 1. Okay. Useful. But I don't want it to equal 1, I want it to equal CE. So now, my Q as a function of time is going to have something of the form CE times 1 minus E. Now, I called it to the minus t. Why not minus 2t? Minus 3t? Pi t. Pi squared E. E to the negative pi squared over E cubed t. Okay? We don't know what that is. I'm going to put a constant there. I'm going to call it A. Just for right now. A couple things that we don't like. Okay? First of all, one reason why we don't like this, there should not be any units up here. Okay? You should never have units in an exponent. So, if t is in seconds, I would expect A to have units of 1 over seconds. If only I could find something that had units of 1 over seconds. Take a look at that. RC, units of RC. This is going to be the ohm farad. Doesn't seem very secondish to me, but follow me. An ohm, okay, remember that's the resistance. So that's going to be voltage over current, so volts per amps. Farad, if we go back to Q equals CE, okay, Q is in coulombs, E is in volts. So C is going to be coulombs per volt. Volts disappear. Units of RC. Coulomb, I know the ampere is the base unit, but whatever. Coulombs per second. Coulombs drop off. Units of RC equal to seconds. Now, we don't want this to be RC so that you get seconds squared. However, Q of t, I'm not going to show you exactly how this works. 1 over RC times t. Okay. This is how the charge builds up on a capacitor. I want you to understand how these differential equations work. You don't have to be able to solve complex differential equations. You could be in fun calc and just take a look at what the function looks like. Okay? We know that we have to end at CE. We know that we have to start off at 0. If I plug in 0 here, okay, I get 1 minus 1, which is 0. Right? Initial charge is 0. If I plug in infinity here, okay, this drops off to 0, I'm left with CE. Okay? That function works. Now, the current through this circuit, okay, current is equal to dq dt. I'll leave this to you to prove for yourselves. But this is going to equal, I just want to cut to the chase here, E over R, E to the negative T over RC. Okay. The voltage across the capacitor is going to equal Q over C, which is going to equal, so if I just take this equation and divide by C, I wind up with E times 1 minus E, negative T over RC. And I'll write it like that instead of the word over RC. Okay. Now, okay, one final thing here, this RC, okay, this is called the time constant. The key with this is you go through, if you go through with the time constants, okay, you get about 63% of the way charged up. Okay. So now, if you plug in T is equal to RC. Okay. So now, let's just take a look at the charge thing. Now this is the time constant. Okay. It's in general called tau. Okay. Tau is equal to RC, it's the time constant. Let's see what happens to charge when I plug in the time constant. Okay. I get CE 1 minus E to the negative RC over RC. Okay. I'm setting Q is T equals tau. Okay, so now I have CE 1 minus E E to the negative 1, and I could call it 1 minus 1 over E. And when you do that, that 1 minus 1 over E get 0.63. So this is equal to 0.63 C. Okay? It is essentially 2/3 of the way charged after one time constant. And you could say, well, plug in for, if you have 2, you don't get necessarily 2/3 more. But you can plug in for 2 time constants, you get 1 minus E to the negative 2, 1 minus E to the negative 3 for 3 time constants, and so on like that. Okay? I'm going to end it there. We're going to take a look at more complex circuits in class tomorrow. That might be helpful. But I wanted to introduce the concept of circuits to you, to RC circuits with you on this. All right? I will see you tomorrow.